So now that we've seen the column perspective on matrix multiplication, let's see another perspective on matrix multiplication. This one is called the row perspective. So this is simply a different formula that gives the same result every time. So again, we need the compatibility condition to be satisfied in order to think about multiplying A by B together. And again, what this diagram is communicating is simply the shapes of the matrices involved. If I want to take A and multiply by B, I need the number of columns of A to be the same as the number of rows of B. And when we multiply A and B together, we produce a new matrix. And the number of rows of that new matrix is the number of rows of A. And the number of columns of that matrix is the number of columns of B. So what does the row perspective say we should do to calculate all of the various entries of A multiplied by B? Well, this is a formula that gives each individual entry of A times B as an inner product of two vectors. So what the row perspective says is that the ij entry of the matrix product A times B is given by an inner product of vectors, and that's the inner product of the ith row of A with the jth column of B. So this sort of contrasts with the column perspective on matrix multiplication, which says, well, if you want to take A and multiply by B, you can use matrix vector products where you take A and then individually multiply by each column of B to build the columns of the product. This perspective says, well, another way you could do it is individually take inner products of each row of A with each column of B and build every entry of the product individually. So let's see how that works with an example. So here we're trying to multiply two matrices together. The matrix on the left is a 4 by 3 matrix, and the matrix on the right is a 3 by 2 matrix. We're certainly allowed to do this because the number of columns of the matrix on the left is the same as the number of rows of the matrix on the right. And so we can multiply these two matrices together. When we do multiply these matrices together, the resulting matrix will have 4 rows because this matrix A on the left here has 4 rows. And it will have 2 columns because this matrix B on the right has 2 columns. So the row perspective on this multiplication says we can now go through and calculate each one of these 8 entries in the product individually by taking inner products. So what about the 1, 1 entry of this new matrix in red here? Well, according to the formula, we're supposed to take the inner product of the first row of A with the first column of B. So remember the mechanics for the inner product are quite simple. We just match up the coordinates, multiply them, and add them together. In this case, we'll get -1 plus 2, which is simply equal to 1. Let's move to a different entry in this product. Now we're looking at the 1, 2 missing entry of our product here. According to the formula for the rows perspective on matrix multiplication, the way we should calculate this entry is by taking the inner product of the first row of A and the second column of B. So again, we're looking at the 1, 2 position. So we take the inner product of the first row of A with the second column of B. When we do the arithmetic here, we end up with -2. Okay, so now let's move to the 2, 1 position. To calculate the 2, 1 position, we should take the inner product of the second row of A with the first column of B. The arithmetic here gives -2. What about the 2, 2 position? Here we should take the inner product of the second row of A with the second column of B. When we do this inner product, we end up with the number -1. Our next missing position is maybe in the 3, 1 position. For the 3, 1 position, we take an inner product of the third row of A with the first column of B. That inner product ends up being 4. Then we take, then to calculate the 3, 2 position, we take an inner product of the third row of A with the second column of B. That inner product ends up just equaling 1. And then for the last 2 entries in our row of the last row of our product, The first one is in the 4, 1 position. So now we take an inner product of the fourth row of A with the first column of B. That's equal to 2. And finally, for the last missing entry, which is in the 4, 2 position, we take an inner product of the fourth row of A with the second column of B, and that ends up equaling 0. So the row perspective allows us to go through entry by entry in our matrix that we're multiplying together, or the product that we're trying to build, and individually calculate every entry. This is how I originally learned matrix multiplication. So out of habit, this is how I do it when I'm doing problems by hand. But as we'll see in the course, the column perspective is equally important, if not more important, in order to understand a lot of the foundational ideas in linear algebra. One thing I'd like to point out is that with this row perspective, keep in mind what we're saying is that when we're taking a matrix A and we're multiplying by a matrix B, every single entry of the product is an inner product of one of the rows of A with one of the columns of B. So the way that works, right, is if we have the first row of A, which I'm depicting as R1 transpose, so I'm calling that the first row of A, and when we multiply it by the first column of B, that produces an inner product. So each individual inner product of the two rows in the first matrix and columns in the second matrix are used to build all of the missing entries of the product. And keep in mind, this can tell you some geometric things about the various vectors in play here. So here I'm depicting the multiplication of a 4 by 5 matrix with a 5 by 3 matrix, which of course should produce a 4 by 3 matrix. One thing, for example, we could point out is that we have a 0 in this product, and that 0 is in the 3, 1 position. So in particular, what this tells me is that whichever inner product I use to build this number or to get this number, the two vectors had to be orthogonal because their inner product was 0. And which two vectors did we take an inner product of to produce this 0? Well, we went to the third row of A with the first column of B. So by mere fact, since someone is just handing us this product, we can just look at this 0 here and we automatically know that whatever the third row of A was, it had to be orthogonal to the first column of B. And you could play similar games here, right? So if the inner product of your two vectors is positive, that means that they form an acute angle. So you could go through here and ask yourself, well, which of these numbers is a positive number? Whichever of these numbers is a positive number, that means they came from an inner product of one of the rows of A, which happens to be acute to one of the columns of B. And if the inner product is negative, that means those two vectors are obtuse. So it's useful just to keep in mind that since we're using inner products from this perspective to build each entry of our matrix product, that actually does contain geometric data. Whether or not that happens to be interesting is a whole other point, but it is there. So the punchline here is we found a 0 in the 3, 1 position, which tells us that the third row of A is orthogonal to the first column of B.